Alright, here's my version of the machine learning hello world exercise. For starters, this is done with the Python 3.5, 3.6 version, not the original one. You can find the link to this repository from here in the README of the original. Here are the configure and run scripts. So there's like two main networks that we asked for. The one with the one hidden layer and the one with the two hidden layers. These configure and run are for the first one, and these are for the second one. Existing configurations can be found from here, and failed pictures will also be dumped here. Okay. Some findings about these. That's right. So these are the main examples, and there really wasn't that big of a difference between them. I expected that the network with more layers could reach better results, but maybe a bit slower. But actually it didn't. It's not really slower. These all reach around the levels they can get in like 10 to 15, 10 to 20 epochs. But as I added layers, the results actually got worse. I think it's probably because with more layers they can get like more specific results, and in the case of like this kind of exercise for them, it can lead to over analyzing. I think it's called like treating noise as signal, and perhaps that's the reason it just gets slightly lower as you add more layers here. On the other hand, when I tried adding more neurons to the one layer, it increased the accuracy a bit. On the other hand, if I added like or had 100 here instead of 50, it didn't really increase the accuracy anymore, so it just reached the maximum of that configuration. As for the learning rate, usually I use the default 3 that was used in the repository material when you load it, as that tended to have the best results. Increasing it a bit like to 5 to 7 or something, or decreasing a bit like maybe 2, didn't really do much. Didn't slow down or get faster, and the accuracy didn't really change. But using something like 10 or more, it started to do a bit of jumping around, so the learning rate was too large and it didn't settle on the optimal values. On the other hand, using something closer to 0, like 0.1, 0.2 or something like that, at that point it started to be noticeably slower. But the accuracy, of course, didn't really change for the good or bad. It perhaps just took a few more epochs to reach the optimal values for that run. Yeah, that's about 40 findings about these. Oh yeah, one more thing about, I mentioned that these reach the somewhat optimal values about as fast. So here are pictures illustrating that, and you can see from here that around epoch 10 to 15 they have already reached pretty good levels. But here the network 2 with 2 hidden layers just kind of gets stuck to the 93 to 94, while the network 1 keeps slowly climbing, maybe like closer to 20 evox until it reaches to the 94 to 95%. Yeah. Then for the code itself here, there's a lot of additional clutter because these same codes are also used in the like original material, the next chapters. There's things like there's entropy and just additional things to improve the stuff, but it's not relevant here, but I did remove the code. But this is what we use here. So here's the loading part. This loader is another script I'll explain in a minute. And here we load the data that will be used. And it's from these here. And then create the network and train it with this SGD function. Explaining those later as well. But let's start with the loading part. So, well, here I added, this could be elsewhere too, but I added the part where it creates the failed folder and removes it and the content before the run. Here's the file loading part with pickle. Pickle is also used to load and save the configurations. This wrapper is used to change the format a bit so it's more convenient. So this here returns, for example, for the training data. It's array with one value for each pixel of the image. And then the second value in the tuple is the like expected result for that picture. So 0 to 9, 1 digit. But here in the wrapper, it's changed for the training data so that the expected result is not 1 digit. It's array of 10 indexes. And there's the expected result. That index is set to 1. That's about the only change here, really. And this here is convenience function that makes the change between the formats. Okay, so let's move on to the network itself. Here are some imports. I added a few of these to create my rendering system here and the file handling things and whatnot. Okay, here's the constructor. This is the size configuration, which is this array here. I also added this predefined variable here that you can set if you want to load an existing configuration when you're already, like when you're creating the network. Otherwise it can just be loaded like this. Okay, sizes is set to these values, of course, and then biases and weights are randomized according to the sizes, so that biases are as here. but important is to note that the first layer is skipped. It doesn't have biases because it's the input layer. So this example as the first network size, here the first one will be 30 for the 30 different biases in this layer, and then the second one is 10 for the different biases in the last. So this is the value the neuron adds when it gets any values, regardless of the other configurations of that value or so. And here's the weights. Also arrays differently so that each is like 2D, 2 arrays. So there's values for, well, these could be thought of as arrays like between the layers. So there's values for both the surrounding layers of this weight. So for example, this size here, the first one will be these two, but just reversed. Okay, let's skip these functions for now. I'll explain the thing itself, starting with the stochastic gradient isn't here. Okay, so it takes the training data, of course. Epochs is the amount of loops it does. Mini batch size, explaining it in a minute. This ETA is learning rate, and then test data can be configured if the user wants to see the progress here during the calculations. Okay, first it does some format things to the data so it can be used, and here's the loop in all the epochs, and creating mini batches from the data after randomizing it. And then the bias and weight calculation is done via these mini batches. And the reason for that is because this, the mini batch here, for example, is size 10. So it optimizes a lot because it needs to calculate a lot less, but results don't really suffer that much. So basically mini batches are like small groups that make the average, or like it is supposed to be the average of the whole, and it is treated as such. And the small errors that are caused by this kind of optimization, there are some algorithms, calculations in here that take those into consideration. Okay, so let's take a look at the update mini batch function next. So here the weights and biases are updated by applying the gradient descent, and the backpropagation algorithm is here, the backprop. So here arrays are initialized, and then it's time to loop through the mini batch, and the backpropagation here returns the gradient delta here for the biases and weights, and those are then applied here. And after those, like looping over the whole mini batch and applying the gradient deltas here, the weights and biases are then changed with those values, or using those values subtracted, so it's trying to minimize the function. And here's the learning rate used and size of the batches for that. Okay, then for the backpropagation algorithm here, this backpropagation, there's like main 4 algorithm things here. So here's the feed forward path list to store all the activations and to store all Z vectors, and then here looping over biases and weights, calculating these using the dot product, which is like simplify the sum which is needed there. After getting the feed forward part here, we get the error handling and rate of change parts here. So this is the part that calculates the error in the output layer, taking it into consideration. As -1 index in Python is the last index here. And then it is applied to the last bias and weights here. And the bias equals to the error, respective one. So it's straight to delta here. But the weight is affected by the previous layer as well, as can be seen here, which is calculated then with the dot again. And here's the loop. And it's essentially doing this same thing, but for the rest of the layers where the algorithm for this error here is slightly different, but still the bias equals to that error, so the delta straightforward, and the weight equals to the similar line here, using the delta and then the activation from the previous layer, calculating the dot from there. And this backpropagation here, it goes through the network layer by layer from the end to the beginning. It's kind of where the name backpropagation comes from. And this is because the cost function is function of the like that uses the values from the next layer in there, and it returns the biases and weights that were then used here as the delta ones. Okay, here's just the cost derivative, aka the derivative of the cost function. And here are the two sigmoid functions that are used in these calculations. Sigmoid itself, and prime here is the derivative of it. And the idea of the sigmoid function is this here, so it's sort of like probability rather than Boolean value. Okay, and here this evaluate is basically just what is used like after training or here to see where the network is at. So when test data is set, it will evaluate after each epoch and see where the network is, how it's doing. And from there I have created this one, which I will explain in a minute, but first let's see the saving and loading here. Well, first here, just ensure that the configuration folder exists because we're saving, and then create the file name in the format that uses the sizes of the network, so you can save multiple configurations for multiple different networks and then use them from there straightforward, and saving it with pickle as a list of lists because these are nested too. Okay, and then load configuration just does that same in reverse. After the file name configuration, it gets the pickle from there. and it's in the list of lists structure. And this feed forward actually, this is what's used in the evaluate. This basically returns the output. Okay, so here's the evaluation with images. So it basically does the same as the other evaluation, but all the failed images are saved in here. Image first, then what number was given by the network and what numbers were expected, and then finally the data from the output neurons. This is to render like the percentage what the network suggested, but we will be looking at that or trying that out soon enough. And this here image is from the PIL library imported up there. So basically, if it fails, create image from the data, save the image to the folder, and append it to the container. And here are the rendering parts. I have this version here where I can navigate the images using keyboard. So when I press arrows, it goes to the next or the previous one and so on. And quit with ESC. Title with the data. You can see how many failed samples there were, which one this is, what number was given, what was expected. And then here are the calculations for the graph, like bar chart, that tells the what the next network thought. It is scaled because the network results don't really add up to one necessarily. So they need to be scaled if you want to treat them as like percentage, like I wanted here in the bar chart. A range of 10, because 10 digits. And here the image is rendered below the chart. And for this keyboard part, it's important to have the interactive so it can be rendered continuously. And here's the same thing but without the keyboard part, so it's just one figure at a time, and when you close it from the X, it will open the next one. Okay, to save some time, I won't be running the configurations in here now, but we will be using the ready configurations. So these here. Let's start with the network 1. Okay, so it reached about 95%, around 500 fail samples. Oh yeah, and these runs use like 2 different sets of images. First the validation data and then the test data. So even if you use the test data or like have set the test data while configuring, so you see continuously how it's doing with that, you can see a bit different results here with the validation data. Okay, here it thought this was 5 instead of 4. a little bit of 9 and 8 as well here. 5 as well, pretty clearly are unanimously. But a bit of 3 here as well. 7 instead of 9. Interesting. Yep. That's for the validation data parts. And here are the test data images. This particle one it's here like every single time. The network just can't comprehend that this would be 5 instead of 6 with these shapes. This is pretty common as well. Also often configured to be 6 instead of 4. Here it's 0, perhaps rectangular 0 or something. Let's see what's in the back part here. Oh, that's an even one, but wrong. There was no doubt whatever in the network that this would not be anything other than 8, but it was wrong. Okay, that was for the network with one hidden layer. Then let's run the other one. A bit lower result, around 1% lower, and about 130 more failed samples here. Okay, and then again this, even with the different network, and it is again given 6, and this one too, this time it's 5. Okay, and like I mentioned earlier, those failed pictures after each run can also be found here for later inspections. Like this is like 63rd failed sample, and it was given 9, not 4, and it was supposed to be 4. Okay, I think that's about it.